There is something quietly thrilling about the idea that life might betray its presence across distances so vast that traveling them remains impossible, that we might detect living worlds without ever leaving our own. Biosignatures represent this possibility, made real. The chemical, physical, and spectral traces that life leaves upon a world simply by existing. Fingerprints that can be read from light years away by those who know what patterns to seek. A biosignature is any observable feature of a planet or moon that suggests biological activity. Any measurable property that life produces and that non-living processes cannot easily replicate. The concept emerges from a simple recognition. Life doesn't just sit quietly, it changes things. It reshapes air and water, creates gases that don't belong, and leaves patterns in the light that passes through its atmosphere. Those changes are what scientists look for. You're listening to the Drowsy Astronaut, where tonight we explore how scientists hope to detect life on worlds orbiting distant stars. The signs and signals that might reveal we are not alone in the cosmos. This journey moves through chemistry and light, through powerful telescopes and careful observation, and through the methods that may one day help answer one of humanity's oldest questions. You can follow along closely if you'd like, or simply let the words settle in the background while you rest or unwind. Either way, the search continues, and we'll follow it wherever it leads. The search for biosignatures begins with understanding what life does to a world. How biology reshapes the chemistry and appearance of a planet in ways that might be visible across interstellar distances. On Earth, life has fundamentally transformed the atmosphere, the oceans, and the land surface over billions of years, leaving signatures that would be detectable by any sufficiently advanced observers watching from afar. The most dramatic of these signatures is oxygen, a gas that comprises roughly 21% of Earth's atmosphere, and that would not exist in such abundance without continuous biological production. Oxygen is extraordinarily reactive, eager to combine with carbon, iron, and countless other elements, meaning that without a constant source replenishing it, atmospheric oxygen would decline to trace levels within geological timescales. On Earth, that source is photosynthesis, the remarkable process by which plants, algae, and cyanobacteria capture sunlight and use its energy to split water molecules, releasing oxygen as a byproduct while incorporating carbon into organic compounds. For over 2 billion years, photosynthetic organisms have pumped oxygen into our atmosphere, maintaining levels that would otherwise be impossible. If we could detect a similar oxygen abundance in the atmosphere of a planet orbiting another star, we would have found something demanding explanation. A chemical condition that screams for a source. Biology would become a serious hypothesis, perhaps the leading hypothesis, though not the only one, as we shall explore later. Oxygen is not the only gas that life produces, and the search for biosignatures considers multiple potential signals that might together paint a picture of a living world. Methane, produced on Earth primarily by microorganisms called methanogens, as well as by larger animals during digestion, represents another biosignature gas that astronomers search for in exoplanet atmospheres. The power of methane as a biosignature increases dramatically when found alongside oxygen, because these two gases react with each other over geological timescales, meaning their coexistence requires ongoing production of both. A planet with significant oxygen and significant methane is not at chemical equilibrium, but is being actively maintained by something. And life is the most compelling explanation we know. Nitrous oxide, another potential biosignature, is produced on Earth primarily by microbial activity in soils and oceans, biological processes that would be difficult to replicate through non-living chemistry. Other gases, hydrogen sulfide, dimethyl sulfide, phosphine, have also been proposed as potential biosignatures under various circumstances, each with its own production mechanisms and interpretive challenges. The search is not for any single gas, but for patterns, for combinations, for the chemical disequilibrium that characterizes a living world. Earth's atmosphere is not at rest, but is continuously maintained by biological activity, a state that passive chemistry would never produce. We look for that same restlessness in the atmospheres of distant worlds. Beyond atmospheric gases, biosignatures can manifest on planetary surfaces in ways that might be detectable across interstellar distances. On Earth, the most prominent surface biosignature is produced by vegetation, which reflects light in a distinctive pattern that would be visible to alien astronomers studying our world. The phenomenon is called the red edge, a sharp increase in reflectivity at the boundary between visible red light and near-infrared wavelengths. Leaves absorb visible light for photosynthesis, using red and blue wavelengths to power the chemical reactions that sustain plant life, but they reflect near-infrared light to avoid absorbing energy that would cause overheating. The result is a dramatic spectral signature, a sudden jump in reflectivity at wavelengths around 700 nanometers that corresponds to no common mineral or geological process. If alien astronomers pointed their instruments at Earth and measured how our planet reflects starlight at different wavelengths, this red edge would appear as evidence of something unusual happening on our surface. Different pigments used by alien photosynthesizers might produce different spectral edges at different wavelengths, meaning the search for surface biosignatures requires openness to patterns we have not specifically predicted. Purple bacteria on early Earth, for instance, used pigments that would produce different signatures than modern green vegetation. The concept of biosignatures extends beyond chemistry and reflectivity to include any observable feature that life might produce and that non-living processes would not. Patterns of seasonal change, for instance, might indicate biological activity if they followed cycles consistent with growth and dormancy, rather than purely physical processes. On Earth, the concentration of carbon dioxide in the atmosphere fluctuates with the seasons as the northern hemisphere's vast forests grow and shed their leaves. A pattern that reflects biological activity rather than geological or atmospheric physics alone. Similar seasonal patterns on an exoplanet might suggest the presence of a biosphere. The structure of light itself can carry biosignature information, as biological molecules often exhibit chirality, a handedness that affects how they interact with polarized light. Earth life uses predominantly left-handed amino acids and right-handed sugars, a preference that influences how polarized light reflects from biological surfaces. If we could measure the polarization of light reflected from an exoplanet and found a preference indicating chiral molecules, this would suggest the presence of biological chemistry. Such measurements are extraordinarily difficult with current technology, but may become possible as instruments improve. The search for biosignatures is not purely theoretical. but is actively underway, with telescopes currently observing promising targets and scientists analyzing data that might contain the first hints of life beyond Earth. The James Webb Space Telescope leads this effort, its infrared sensitivity allowing detection of molecules that previous instruments could not observe. The technique that makes biosignature detection possible is called transit spectroscopy, a method that analyzes starlight after it has passed through a planet's atmosphere. When a planet crosses in front of its star from our perspective, a tiny fraction of the starlight filters through the planet's atmospheric envelope before continuing toward Earth. Different gases absorb different wavelengths of light in characteristic patterns, leaving fingerprints in the spectrum that reveal what the atmosphere contains. By comparing the spectrum during transit to the spectrum when the planet is not blocking any starlight, astronomers can determine what molecules are present and in what abundances. This technique has already detected water vapor, carbon dioxide, and methane in the atmospheres of various exoplanets, demonstrating that the chemistry of life's building blocks exists beyond our solar system. The next step is detecting combinations of gases that suggest not just chemistry but biology. The search requires patience because the signals are small and the observations demanding. A planet's atmosphere absorbs only a tiny fraction of the light passing through it, meaning biosignature detection requires extraordinary precision and long observation times to build up sufficient signal above the noise. Current telescopes can detect atmospheric features on large planets orbiting close to their stars, where the geometries favor detection and the atmospheric signals are strongest. Earth-sized planets in the habitable zones of sun-like stars present greater challenges. Their smaller atmospheres and less frequent transits making detection more difficult. Yet the technology continues to improve, and what seems barely possible today may become routine within a generation. The telescopes being planned and built will push sensitivity to levels that current instruments cannot achieve, potentially bringing dozens or hundreds of nearby worlds within reach of biosignature searches. The question of whether we are alone in the universe may be answerable within our lifetimes, or it may require centuries of additional work. The uncertainty itself is part of the endeavor, the not knowing that motivates continued observation and analysis. The fingerprints of life may already be present in data we have collected, waiting for recognition, or they may require instruments we have not yet built. Either way, the search continues, and in the next part we will explore how our own planet would appear to distant observers seeking biosignatures. The best way to understand what biosignatures we might find on other worlds is to consider what alien astronomers would detect if they turned their instruments toward Earth, the one planet we know for certain hosts life. Our world provides a template for what a living planet looks like from the outside. If observers located in a star system tens of light years away pointed their telescopes at the sun and waited for Earth to transit, they would first notice a small dip in the sun's brightness as our planet passed in front of the stellar disk. The dip would be tiny, roughly 1 part in 10,000, but detectable with sufficiently precise instruments. As Earth crossed the sun, some sunlight would pass through our atmosphere before continuing toward those distant observers. This light would carry the fingerprints of every gas it encountered, absorption features at specific wavelengths that would reveal what our atmosphere contains. The observers would detect oxygen at roughly 21% abundance, an enormous amount of this reactive gas that would immediately demand explanation. They would detect nitrogen as the dominant atmospheric component, along with traces of carbon dioxide, water vapor, methane, nitrous oxide, and other gases in various concentrations. The combination of oxygen and methane would be particularly striking to scientifically sophisticated observers, because these gases react with each other and should not coexist in significant quantities unless something is continuously producing both. The observers would recognize that Earth's atmosphere is not in chemical equilibrium, but is being actively maintained. This chemical disequilibrium is a hallmark of life, a condition that physics alone does not produce. A dead world's atmosphere reaches equilibrium and stays there. A living world's atmosphere is continuously churned by biological activity that prevents equilibrium from ever being achieved. The alien astronomers would also detect water vapor in our atmosphere, indicating that liquid water exists somewhere on our surface, a requirement for life as we understand it. The combination of water, oxygen, methane, and chemical disequilibrium would paint a compelling picture of a world where something interesting is happening. If their instruments were sensitive enough, they might detect even more specific biosignature gases like dimethyl sulfide, produced on Earth almost exclusively by marine microorganisms, or nitrous oxide, produced by bacterial activity in soils. Each additional biosignature would strengthen the case that Earth hosts biology. Beyond atmospheric spectroscopy, alien observers might study how Earth reflects sunlight at different wavelengths, looking for patterns that reveal surface conditions. This technique, called reflectance spectroscopy, can provide information about a planet's surface composition even from tremendous distances. The most prominent surface biosignature Earth presents is the red edge of vegetation. The sharp increase in reflectivity, where visible red light transitions to near-infrared. Roughly 30% of Earth's land surface is covered by vegetation, enough to produce a detectable signal in the planet's overall reflectance spectrum. The alien astronomers would see that Earth reflects red and infrared light differently than any common rock or mineral, suggesting the presence of something unusual on the surface. If they understood biology, they might recognize this pattern as consistent with photosynthetic pigments designed to harvest visible light while avoiding infrared heating. They might also detect the glint of sunlight reflecting off Earth's oceans, a specular reflection that indicates large bodies of liquid water on the surface. This observation would complement the atmospheric water vapor detection, confirming that water exists in liquid form at the surface. The reflectance of Earth varies with rotation as different portions of the surface come into view. Continents and oceans and ice caps, each contributing their own spectral signatures. Careful analysis of these rotational variations might reveal the presence of distinct surface features even without resolving them directly. The alien observers might detect seasonal variations in Earth's reflectance and atmospheric composition, patterns that follow annual cycles consistent with biological activity. The carbon dioxide concentration fluctuates as northern hemisphere forests grow and shed leaves. The overall reflectance changes as snow cover expands and retreats. These temporal variations would provide additional evidence that something dynamic is happening on Earth. Processes that go beyond the slow changes of geology or the regular patterns of purely physical climate cycles. Life introduces variability on timescales that geology does not typically produce. If the alien astronomers possessed technology comparable to what we are developing, They might even detect the faint glow of artificial lights on Earth's night side. Concentrations of illumination that follow the patterns of human settlement. This would be a technosignature rather than a biosignature, evidence not just of life, but of technological civilization. The radio emissions from Earth would also be detectable by sufficiently sensitive instruments, our television and radar and communication signals leaking into space and traveling outward at the speed of light. These artificial electromagnetic emissions have a character quite different from natural radio sources. Natural radio sources produce emissions across broad frequency ranges, with patterns determined by physics. The synchrotron radiation of electrons spiraling in magnetic fields, the thermal emission of hot gas, the pulses of rotating neutron stars. Artificial emissions are concentrated in narrow frequency bands, modulated in ways that encode information, structured rather than random. An alien civilization detecting Earth's radio emissions would recognize them as artificial, as products of technology rather than nature. Combined with the biosignatures in our atmosphere and on our surface, the picture would be complete. Earth is not just a living world, but a world with intelligent inhabitants. This is how we appear to the cosmos, a pale blue dot broadcasting its aliveness through chemistry and light and radio waves. Every biosignature detection technique we apply to other worlds could be applied to Earth, and we would be found. The thought experiment of viewing Earth from outside helps calibrate our expectations for what we might find elsewhere. Not every living world would look exactly like Earth, of course, as different biospheres might use different metabolisms and produce different biosignatures. A planet dominated by photosynthetic organisms, using different pigments than chlorophyll, would show different spectral features. Perhaps a purple edge or a yellow edge rather than our familiar red edge. A world where life had not invented oxygen-producing photosynthesis might lack atmospheric oxygen entirely while still hosting abundant biology. Planets around red dwarf stars would receive different spectra of light than Earth receives from the Sun, potentially favoring different photosynthetic pigments and producing different surface signatures. The habitable zones around such stars lie closer in, changing the geometry of transit observations and the conditions that life would face. The diversity of potential biosignatures reflects the diversity of potential biospheres. The many ways that life might solve the problems of energy capture and metabolism and survival. We search not for exact copies of Earth, but for any signal that suggests biology, whatever form that biology might take. Our planet demonstrates that biosignatures can be strong and unmistakable when life has had billions of years to transform its world. Earth's atmosphere did not always contain abundant oxygen. The rise of photosynthesis and the subsequent Great Oxidation Event fundamentally changed our planet's chemistry roughly 2.4 billion years ago. Before that transformation, Earth would have presented different biosignatures to any observers, perhaps methane from methanogenic organisms, perhaps other gases we have not considered. The biosignatures we now display are the products of a particular evolutionary history, not inevitable, but contingent. This history reminds us that biosignature detection is time-dependent, that a planet might host life for billions of years before producing detectable atmospheric signatures. Young biospheres, or biospheres using different metabolisms, might be harder to detect than Earth's current mature oxygenic biosphere. The search for biosignatures is therefore a search for worlds where life has not only emerged, but has had sufficient time and opportunity to transform its environment in ways we can detect. Such worlds may be common or rare. We do not yet know. But the search itself teaches us what to look for and how to look. In the next part, we will explore the specific worlds that scientists are currently watching, the real targets where biosignature searches are actively underway. The search for biosignatures focuses on specific worlds that scientists consider most promising for harboring life. Real planets and moons with names and coordinates that telescopes are currently observing. These are not abstract possibilities, but concrete targets, places where the detection of life might occur within our lifetimes. The TRAPPIST-1 system has become one of the highest priority targets for biosignature searches. A compact planetary system located approximately 40 light-years from Earth, in the constellation Aquarius. 7 Earth-sized rocky planets orbit an ultra-cooled red dwarf star, with several of them receiving enough stellar warmth to potentially maintain liquid water on their surfaces. The planets are designated by letters from B through H, with planets D, E, and F orbiting in or near the star's habitable zone, the region where temperatures might allow liquid water to exist. These 3 worlds receive particular attention because liquid water is considered essential for life as we understand it. The compactness of the TRAPPIST-1 system makes it ideal for transit spectroscopy, as the planets pass frequently in front of their small star and their atmospheres occult a relatively large fraction of the stellar disk. The James Webb Space Telescope has already observed several TRAPPIST-1 planets, and the analysis of these observations continues. K218b, located approximately 124 light-years from Earth in the constellation Leo, represents another high-priority biosignature target that has already yielded intriguing results. This world is larger than Earth, but smaller than Neptune, a category called a sub-Neptune that has no analogue in our solar system. Observations by the James Webb Space Telescope detected carbon dioxide and methane in the atmosphere of K218b, along with a possible detection of dimethyl sulfide, a molecule that on Earth is produced almost exclusively by marine life. The dimethyl sulfide detection remains preliminary and contested, but it represents exactly the kind of signal that biosignature searches hope to find. The planet may be a Hycean world, a type of planet with a hydrogen-rich atmosphere, overlying a global liquid water ocean. Such worlds might be habitable despite conditions quite different from Earth's, offering a different template for where life might arise. The K218b observations demonstrate that biosignature searches are not merely theoretical, but are actively underway, generating data that scientists analyze for hints of biological activity. Whether the current hints will survive scrutiny and additional observation remains to be seen. Proxima Centauri b orbits the closest star to our Sun, a red dwarf located just 4.2 light-years away, making it the nearest known exoplanet and a natural target for biosignature searches. The planet orbits within its star's habitable zone, receiving enough warmth to potentially maintain liquid water. The proximity of Proxima Centauri b makes it an attractive target for future observations, though the planet does not transit its star from Earth's perspective, limiting the techniques available for atmospheric study. Direct imaging or other approaches will be needed to characterize this nearby world. The planet faces challenges for habitability, including the high activity level of its red dwarf host star, which produces frequent flares that might strip away atmospheres or sterilize surfaces. Whether Proxima Centauri b has retained an atmosphere capable of supporting life remains unknown. Despite these uncertainties, the planet's proximity ensures it will remain a focus of interest as observational capabilities improve. A biosignature detection on the nearest exoplanet would be particularly significant, suggesting that life might be common throughout the galaxy. Within our own solar system, several worlds present opportunities for biosignature detection much closer to home. Targets that spacecraft might visit and sample directly, rather than studying from afar. Mars remains the most accessible and most studied of these targets. Rovers currently operating on the Martian surface search for signs of past or present life, analyzing rocks and sediments for organic molecules, isotopic ratios, and mineralogical features that might indicate biological activity. The Perseverance rover is collecting samples that a future mission will return to Earth for detailed laboratory analysis. Mars almost certainly hosted liquid water on its surface in the distant past, and the question of whether life arose during that wet period remains open. If life did emerge on early Mars, it might have left fossils or chemical traces in the rock record, biosignatures preserved for billions of years waiting to be discovered. The Martian subsurface might even host present-day life, organisms that retreated underground as the surface became cold and dry, surviving in aquifers or ice deposits where liquid water might still exist. Detecting such life would require drilling or other access to the subsurface, capabilities that future missions might provide. Europa, a moon of Jupiter, hides a global ocean of liquid water beneath a shell of ice, a vast reservoir that contains more water than all of Earth's oceans combined. This subsurface ocean represents one of the most promising environments for life in our solar system, a place where the essential ingredients for biology might all be present. The ocean is kept liquid by tidal heating, the gravitational flexing of Europa's interior as the moon orbits Jupiter, which generates enough warmth to prevent the ocean from freezing solid. Hydrothermal vents on the ocean floor might provide energy and chemicals that life could exploit, similar to the ecosystems around hydrothermal vents in Earth's deep oceans. NASA's Europa Clipper mission, launched in October 2024, will study Europa in detail during multiple flybys, characterizing the ice shell, the ocean beneath, and the processes occurring at the surface. The spacecraft will not directly sample the ocean, but will search for signs of habitability and potential biosignatures. The surface of Europa is geologically young, refreshed by ice from below, meaning that material from the ocean might be accessible at or near the surface. Organic molecules or other biosignatures originating in the ocean might be detectable without actually penetrating the ice shell. Enceladus, a small moon of Saturn, has revealed itself to be surprisingly active, with geysers at its south pole spraying water ice and vapor into space from a subsurface ocean. These plumes offer a remarkable opportunity for biosignature detection, as the moon is essentially providing free samples of its interior. The Cassini spacecraft flew through Enceladus's plumes multiple times during its mission, detecting water, salts, organic molecules, and molecular hydrogen, chemicals consistent with hydrothermal activity in the subsurface ocean. The hydrogen is particularly intriguing, as it could provide energy for microbial life through chemical reactions similar to those used by some Earth organisms. A future mission to Enceladus could fly through the plumes with instruments specifically designed to detect biosignatures, searching for amino acids, lipids, or other molecules that life produces. Such a mission could potentially detect life without ever landing, simply by sampling what the Moon naturally ejects. The accessibility of Enceladus's ocean, combined with the tantalizing chemical hints already detected, makes this small moon one of the most exciting targets for biosignature searches in the solar system. Titan, Saturn's largest moon, offers a different kind of possibility. A world with a thick atmosphere and liquid bodies on its surface, but where the liquids are methane and ethane rather than water. Life on Titan, if it exists, would be fundamentally different from Earth life, using different chemistry in a much colder environment. The presence of complex organic molecules on Titan, synthesized by photochemistry in the Moon's atmosphere, provides raw materials that some form of life might conceivably exploit. Whether biology could function at Titan's frigid temperatures remains an open question that future exploration might address. The Dragonfly mission, scheduled to arrive at Titan in the mid-2030s, will explore the Moon's surface and atmosphere, characterizing its chemistry and searching for signs of prebiotic processes or even biosignatures. Titan represents our chance to explore a truly alien world, one where the rules of habitability might differ from what we know. Each of these targets offers a different opportunity for biosignature detection, different environments where life might arise, and different challenges for observation. The search proceeds on multiple fronts simultaneously, increasing the chances that at least one will yield a discovery. In the next part, we will explore the tantalizing hints that have already emerged from biosignature searches, the signals that demand further investigation. The search for biosignatures has not yet yielded a confirmed detection of life beyond Earth, but it has produced tantalizing hints. Signals that fall short of proof, but that demand continued investigation and careful analysis. These glimpses represent the frontier of the search, the boundary between what we know and what we are still trying to determine. The possible detection of dimethyl sulfide on K218b, announced in September 2023, represents perhaps the most intriguing hint to emerge from exoplanet atmosphere studies. Dimethyl sulfide is a molecule that on Earth is produced almost exclusively by phytoplankton and other marine organisms, making its presence on another world potentially significant. The James Webb Space Telescope detected spectral features in the atmosphere of K218b that are consistent with dimethyl sulfide absorption, though the detection remains tentative and the subject of ongoing debate within the scientific community. The signal is near the threshold of detectability, meaning that additional observations will be needed to confirm or refute its presence. If confirmed, the dimethyl sulfide detection would not prove that life exists on K218b, as scientists would need to consider whether non-biological processes could produce the same molecule under the conditions that exist on that world. But it would elevate the planet to the highest priority for follow-up observations. The detection of methane on Mars has generated decades of controversy, with some observations suggesting the presence of this potential biosignature and others failing to detect it at all. Methane in the Martian atmosphere would be significant because it should be destroyed by solar radiation within a few hundred years, meaning any detection implies ongoing production. The Curiosity rover detected spikes of methane at its landing site in Gale Crater, with concentrations varying seasonally and spiking occasionally to levels 10 times the background. The European Space Agency's Trace Gas Orbiter, however, has failed to detect methane from orbit, creating a puzzle that scientists are still working to resolve. If methane is truly present on Mars and is being continuously produced, the source could be either biological or geological. Methanogenic microorganisms in the subsurface could produce methane as a metabolic byproduct, but so could certain geological processes involving water reacting with olivine-rich rocks. The Mars methane mystery remains unsolved, neither confirming nor ruling out the presence of life, but highlighting the complexity of biosignature interpretation, even when we have extensive data about the planet in question. The detection of phosphine in the atmosphere of Venus, announced in September 2020, generated enormous excitement, followed by significant controversy. Phosphine is a molecule that on Earth is produced primarily by living organisms or by industrial processes, making its presence on Venus potentially extraordinary. The initial detection, based on spectroscopic observations from ground-based telescopes, suggested phosphine concentrations of roughly 20 parts per billion in the Venusian clouds, far more than any known photochemical or geological process could explain. If real, the detection would imply either unknown chemistry or biological production. Subsequent analysis challenged the detection, with some scientists arguing that the spectral feature attributed to phosphine might instead be sulfur dioxide, a common volcanic gas on Venus, or that the data processing had introduced artifacts. The debate continues, with additional observations planned and the original detection neither fully confirmed nor fully refuted. Whether or not phosphine exists in the Venus atmosphere, the episode illustrates both the excitement and the challenges of biosignature detection. The way that tantalizing hints must be scrutinized carefully before conclusions can be drawn. The Cassini spacecraft's fly-throughs of Enceladus's plumes detected molecular hydrogen, a potential biosignature that could indicate hydrothermal activity in the Moon's subsurface ocean. On Earth, hydrogen-rich hydrothermal vents support ecosystems based on chemosynthesis, organisms that derive energy from chemical reactions rather than sunlight. The hydrogen detected by Cassini is consistent with ongoing reactions between water and rock at the bottom of Enceladus's ocean. Reactions that would release both hydrogen and chemical energy. Whether any organisms are present to exploit this energy source remains unknown, but the conditions appear suitable. Cassini also detected complex organic molecules in the plumes, compounds with masses suggesting molecular structures rather than simple inorganic chemistry. These organics could be products of non-biological chemistry, but they could also be biosignatures, the debris of organisms living in the ocean below. The Enceladus detections are not biosignature confirmations, but rather indications that the ingredients for life, water, energy, organic chemistry, are present. A future mission designed specifically for biosignature detection could potentially resolve whether those ingredients have combined into biology. The search for biosignatures on Mars by rovers has yielded both intriguing hints and frustrating ambiguities. The Viking landers of the 1970s conducted experiments designed to detect metabolic activity in Martian soil, with results that remain controversial to this day. The Viking-labeled release experiment produced positive results initially, with the Martian soil appearing to consume nutrients in a way consistent with biological activity. However, other experiments on the same soil found no evidence of organic molecules, creating a puzzle that has never been satisfactorily resolved. Most scientists now interpret the Viking results as products of unusual Martian soil chemistry rather than biology. But a minority continue to argue that the labeled release experiment may have detected life. The ambiguity highlights the difficulty of designing experiments that can distinguish biological activity from mimicking chemistry. More recent rovers have detected organic molecules in Martian rocks, including compounds like thiophene and benzene that could be produced by biology, but could also result from non-biological processes. The presence of organics confirms that the chemistry of life's building blocks exists on Mars, but does not confirm that life itself is or was present. The search for biosignatures in ancient Earth rocks provides useful lessons for interpreting potential biosignatures on other worlds. Scientists studying rocks billions of years old have developed techniques for recognizing signs of ancient life, techniques that might someday be applied to Martian samples. Certain isotopic ratios, particularly in carbon and sulfur, can indicate biological processing, as living organisms preferentially use lighter isotopes in their metabolic reactions. Stromatolites, layered rock structures produced by microbial mats, preserve evidence of ancient life in their physical form, rather than their chemistry. Microfossils, the preserved remains of ancient microorganisms, provide direct evidence of past life if they can be distinguished from mineral structures that might mimic biological shapes. This distinction can be challenging even for Earth rocks, where we know life existed, and would be even more challenging for rocks from another world. The techniques developed for ancient Earth biosignatures are being refined for application to Mars samples and potentially to material from other worlds. The Perseverance rover is currently collecting samples that will eventually be returned to Earth for the most detailed analysis possible. Each tantalizing hint that has emerged from biosignature searches represents both promise and caution. The possibility that we are seeing the first signs of life beyond Earth, and the recognition that alternative explanations must be carefully considered. The hints accumulate, none yet conclusive, all demanding further investigation. The scientific community approaches potential biosignature detections with appropriate skepticism, recognizing that extraordinary claims require extraordinary evidence. A confirmed detection of life beyond Earth would be among the most significant discoveries in human history, and the bar for such confirmation is correspondingly high. Yet the hints suggest that we are looking in the right places with the right methods, that the search for biosignatures is a reasonable approach to the question of whether life exists beyond Earth. Each inconclusive detection refines our understanding of what to look for and how to interpret what we find. The search continues, And in the next part, we will explore a special category of biosignatures, the signs not just of life, but of intelligent, technological life. The search for biosignatures encompasses all signs of life, from the simplest microbes to the most complex organisms. But a specialized subset of this search focuses specifically on the signatures that technology produces. Technosignatures would indicate not just living worlds, but worlds inhabited by intelligent beings who have developed the capacity to modify their environments and emit signals into space. The distinction between biosignatures and technosignatures matters because technology might be easier to detect in some ways than simple biology. A civilization's industrial activity could produce atmospheric changes more dramatic than any microbial process, and deliberate signals intended for interstellar communication could be designed to stand out against natural backgrounds. Earth itself produces numerous technosignatures that would be detectable by sufficiently advanced observers at interstellar distances. Our radio and television transmissions, our radar systems, our satellite communications, all leak electromagnetic radiation into space, creating an expanding bubble of signals that has now reached stars dozens of light years away. These artificial emissions differ from natural radio sources in their spectral characteristics, their modulation patterns, and their association with a planet, rather than with stars or other natural emitters. An observer who knew what to look for could recognize these signals as artificial, as products of technology rather than astrophysical processes. The search for extraterrestrial intelligence, known by the acronym SETI, has focused primarily on detecting radio signals from other civilizations, scanning the sky for transmissions that might indicate intelligent life elsewhere in the galaxy. This search has continued for over 60 years without a confirmed detection, but the null result does not prove that intelligence is absent. The challenge with radio SETI is the vastness of the search space. The number of stars that might host civilizations, the range of frequencies they might use, the directions they might transmit, the times they might be active. We have surveyed only a tiny fraction of the possibilities, meaning that even abundant civilizations might have escaped detection so far. Modern SETI searches use sophisticated algorithms to distinguish potential artificial signals from the many natural and human-made sources of radio interference. A true extraterrestrial signal would need to pass numerous tests. Consistency across multiple observations, movement consistent with a source beyond Earth, patterns that natural processes could not produce. The Breakthrough Listen project, funded by private donations, represents the most comprehensive SETI search ever conducted, surveying nearby stars and nearby galaxies across a wide range of radio frequencies. The search continues to accumulate data, with analysis ongoing and the possibility of detection always present. Beyond radio signals, technosignatures might manifest in ways that overlap with the biosignature searches conducted by exoplanet astronomers. A technological civilization might alter its planet's atmosphere in ways detectable through transit spectroscopy, producing chemical fingerprints that biology alone would not create. Chlorofluorocarbons, the industrial chemicals responsible for Earth's ozone hole, have no known natural sources and would be detectable in an exoplanet atmosphere if present in sufficient quantities. A planet with CFCs in its atmosphere would almost certainly host a technological civilization. as no biological or geological process produces these compounds. Nitrogen dioxide, produced on Earth primarily by combustion in vehicles and power plants, represents another potential technosignature that might be detectable in exoplanet atmospheres. The presence of industrial pollutants would indicate not just life, but civilization. Not just organisms, but technology. The James Webb Space Telescope and future instruments might detect such industrial signatures in the atmospheres of nearby exoplanets. Though the concentrations would need to be much higher than on Earth for detection to be feasible. A highly industrialized planet, or one where civilization had not yet implemented pollution controls, might be more detectable than Earth. Artificial structures on a planetary scale could produce detectable signatures, though building such structures would require technological capabilities far beyond what humanity currently possesses. The concept of a Dyson sphere, a structure that captures most or all of a star's energy output, has been proposed as a potential technosignature. A complete Dyson sphere would be invisible at optical wavelengths, as it would absorb all the star's visible light, but it would glow brightly in infrared as it radiated the absorbed energy as waste heat. Searches for stars that are unexpectedly bright in infrared or unexpectedly dim in visible light have been conducted, though no convincing Dyson sphere candidates have been identified. More modest structures, like swarms of satellites or space habitats, might produce subtle effects on the light from their host stars. Periodic dimming patterns or spectral features that careful observation could detect. The search for such structures remains speculative, as we do not know what forms alien megastructures might take. The anomalous dimming of Boyajian's star, which showed irregular brightness variations unlike any known astrophysical phenomenon, briefly excited speculation about artificial structures before more mundane explanations involving dust were found to fit the data. The episode illustrated both the challenges and the excitement of the search for technosignatures. Artificial illumination on a planet's night side could indicate cities or other infrastructure. A technosignature that would be extraordinarily difficult to detect at interstellar distances, but that might become accessible with future telescopes. Earth's night side shows clear evidence of artificial lighting, concentrated in patterns that follow human population density. A sufficiently advanced telescope might detect the integrated light from an alien civilization's cities, distinguishing it from natural sources by its spectral characteristics and its association with the planet's dark hemisphere. Such a detection would provide unmistakable evidence of intelligent life. Laser emissions represent another potential technosignature, either as deliberate signals intended for interstellar communication or as leakage from technological applications we might not anticipate. Lasers can be extraordinarily bright at specific wavelengths, potentially outshining stars for brief moments in narrow spectral bands. Optical SETI searches look for such laser pulses, scanning stars for brief flashes that natural processes would not produce. The search complements radio SETI, covering different portions of the electromagnetic spectrum where civilizations might choose to communicate. The absence of detected technosignatures, despite decades of searching, raises questions about the prevalence of technological civilizations in the galaxy, a puzzle known as the Fermi paradox. If intelligent life is common, why have we not detected its signals? The question has many possible answers, each with different implications for the search. Perhaps technological civilizations are rare, arising infrequently even on planets that host life. Perhaps they are common but short-lived, destroying themselves or abandoning technology before spreading through the galaxy. Perhaps they exist but use communication methods we have not thought to look for. Or perhaps they are simply too far away for their signals to have reached us yet. Alternatively, perhaps our searches have simply not been comprehensive enough, missing signals that exist because we looked in the wrong places at the wrong times with insufficient sensitivity. The null result constrains but does not eliminate the possibility that intelligence is common. The search for technosignatures continues alongside the search for biosignatures, two complementary approaches to the question of whether we are alone. In the next part, we will explore the primary tool currently conducting both searches: the James Webb Space Telescope. The James Webb Space Telescope represents the most powerful tool humanity currently possesses for searching for biosignatures on worlds orbiting other stars. An instrument designed for many purposes, but exquisitely suited to analyzing the atmospheres of distant planets. Its capabilities far exceed those of any previous telescope for this particular application. The telescope was launched in December of 2021. Placed into orbit around the second Lagrange point, approximately 1.5 million kilometers from Earth, where it operates in the perpetual shadow of a tennis court-sized sunshield that keeps its instruments at temperatures approaching absolute zero. This extreme cold is essential for detecting the faint infrared signals from exoplanet atmospheres. The primary mirror spans 6.5 meters, composed of 18 hexagonal segments coated in gold to optimize reflectivity in the infrared wavelengths, where many important molecules have their strongest absorption features. The gold coating gives the telescope its distinctive appearance, a honeycomb of golden mirrors that has become iconic in images of the instrument. 4 scientific instruments analyze the light collected by the primary mirror, each specialized for different types of observations. For biosignature searches, the most relevant are the spectrographs that can spread light into its component wavelengths, revealing the absorption features that indicate which molecules are present. The technique that makes biosignature detection possible is transit spectroscopy, and the James Webb Space Telescope has refined this technique to unprecedented precision. When an exoplanet passes in front of its star, Webb can measure the spectrum of starlight that filters through the planet's atmosphere with extraordinary accuracy. The changes in the spectrum during transit are tiny, perhaps a few parts in 10,000 at the wavelengths where atmospheric molecules absorb. Detecting such small changes against the noise and variability of stellar light requires both exquisite instrumental sensitivity and sophisticated data analysis techniques. Webb has already demonstrated its capabilities by detecting water vapor, carbon dioxide, methane, and sulfur dioxide in the atmospheres of various exoplanets, establishing that the chemistry of life's essential elements exists beyond our solar system. These detections confirm that the technique works and that biosignature gases could potentially be found. The telescope has observed several of the TRAPPIST-1 planets, beginning to characterize their atmospheres and constrain what molecules might be present. Early results suggest that some of the inner planets may have lost their atmospheres baked away by their red dwarf star. But observations of the potentially habitable outer planets continue. The observation of K2-18b, that revealed the possible dimethyl sulfide signature, demonstrates what Webb can achieve, and also its limitations. The detection pushed the telescope's capabilities to their limits, with the signal just barely distinguishable from noise and systematic effects. Additional observations of K218b are planned, accumulating more data to either confirm or refute the tentative detection. If the dimethyl sulfide signal holds up, it would represent the most compelling biosignature hint yet obtained from an exoplanet, though still not proof of life. The telescope must balance biosignature searches against its many other scientific priorities, from studying the earliest galaxies to observing the formation of stars and planets to characterizing objects within our own solar system. Observation time is allocated through a competitive proposal process, with biosignature targets representing a fraction of the overall program. Scientists around the world are analyzing Webb data as it becomes available, applying different techniques and approaches to extract the maximum information from each observation. The search for biosignatures is a collaborative effort involving many research groups with complementary expertise. The infrared sensitivity of the James Webb Space Telescope opens windows that previous instruments could not access. Wavelength ranges where important molecules have diagnostic absorption features. Carbon dioxide, water, methane, ammonia, and many other molecules absorb strongly at infrared wavelengths that Webb can observe. The telescope can detect ozone, a molecule produced in Earth's atmosphere by the photochemical processing of biological oxygen, providing an indirect indicator of oxygen, even when oxygen itself is difficult to detect directly. Ozone has strong absorption features in the mid-infrared, a region where Webb excels. Dimethyl sulfide and other complex organic molecules also have infrared signatures that Webb can potentially detect, though at the very edge of its capabilities for the small planets in habitable zones that are of greatest interest. Each new observation pushes understanding of what is possible. The telescope's capabilities will not be exceeded until the next generation of instruments comes online, a transition that may not occur for a decade or more. For the foreseeable future, Webb represents our best hope for detecting biosignatures on potentially habitable exoplanets. The observation strategy for biosignature searches involves accumulating multiple transits of the same planet, building up signal-to-noise ratio with each additional observation. A single transit provides limited information, but 10 or 20 transits can reveal atmospheric features that would otherwise remain hidden. For planets that transit frequently, this accumulation can happen relatively quickly. TRAPPIST-1 planets orbit their star in just a few days, meaning opportunities for observation are plentiful. K218b, with its 33-day orbital period, transits less frequently, making data accumulation slower. Earth-like planets in the habitable zones of Sun-like stars present the greatest challenge, as their orbital periods are measured in hundreds of days and their stars are large, meaning the atmospheric signal is proportionally smaller. Such planets remain largely beyond Webb's reach, awaiting future telescopes with greater capabilities. The telescope continues to operate, gathering data that will be analyzed for years to come, potentially containing hints or even confirmations of biosignatures that we have not yet recognized. The search unfolds in something close to real time, with each observation adding to our understanding. The legacy of the James Webb Space Telescope for biosignature searches will depend on what its observations reveal. discoveries that may not be fully recognized until years of data have been accumulated and analyzed. The telescope is writing a story whose ending we do not yet know. Even if Webb does not detect confirmed biosignatures, it will have demonstrated the technique and shown what future telescopes will need to achieve, establishing the parameters for next-generation instruments that might succeed where current capabilities fall short. The search for life beyond Earth is a multi-generational endeavor, and Webb represents one generation's contribution to a project that will continue long after its mirrors have cooled and its instruments have fallen silent. The data it gathers will be analyzed for decades. In the next part, we will explore in greater detail how transit spectroscopy works, the elegant technique that allows telescopes like Webb to read the chemical composition of atmospheres across light years of space. The detection of biosignatures on distant worlds relies on a technique that seems almost magical in its power, using the light of a star to read the composition of a planet's atmosphere from light years away. Transit spectroscopy transforms starlight into a chemical census of worlds we cannot visit. The basic concept is deceptively simple. When a planet passes in front of its star from our perspective, a tiny fraction of the starlight passes through the planet's atmosphere before continuing toward Earth. This light carries information about what it encountered during that brief passage, encoded in the wavelengths that were absorbed along the way. Different molecules absorb light at different wavelengths, each species leaving its own characteristic fingerprint in the spectrum. Carbon dioxide absorbs at certain infrared wavelengths, water at others, methane at still others. By measuring which wavelengths are absorbed more strongly during transit, astronomers can determine what molecules the atmosphere contains. The fraction of starlight that passes through the atmosphere is extraordinarily small, perhaps 1 part in 10,000 or less, making the measurement extremely challenging. The atmospheric signal must be extracted from much larger variations in stellar brightness caused by the star's own activity, instrumental effects, and other noise sources. The spectrum of a star is not uniform, but contains absorption features of its own. Dark lines at specific wavelengths where gases in the stellar atmosphere absorb light before it leaves the star. These stellar features are much stronger than any planetary atmospheric signal, requiring careful modeling and subtraction. By comparing spectra taken during transit to spectra taken when the planet is not in front of the star, astronomers can isolate the contribution of the planetary atmosphere. The comparison reveals the additional absorption that occurs only when starlight passes through the planet's atmospheric shell. The depth of absorption at each wavelength reveals not just which molecules are present, but how abundant they are. Stronger absorption indicates higher concentrations, allowing astronomers to estimate the mixing ratios of different gases in the atmosphere. These abundances provide crucial context for biosignature interpretation. The altitude distribution of molecules can also be inferred, as absorption at different wavelengths probes different levels of the atmosphere. Molecules concentrated in the upper atmosphere produce different signatures than molecules well mixed throughout, providing three-dimensional information about atmospheric structure. The geometry of transit observations imposes constraints on which planets can be studied and how much information can be obtained. Only planets whose orbits happen to be aligned so that they cross in front of their stars as seen from Earth can be studied with this technique, a fraction that depends on orbital inclination. For randomly oriented orbits, the probability of transit alignment decreases with orbital distance, meaning planets closer to their stars are more likely to transit. Fortunately, the habitable zones of small red dwarf stars lie close in, making potentially habitable planets around these stars relatively accessible. The size of the planet relative to its star affects the strength of the atmospheric signal, with larger planets around smaller stars producing proportionally stronger signals. Earth-sized planets around Sun-like stars present the greatest challenge. Their tiny atmospheres blocking a very small fraction of the large stellar disk. The frequency of transits depends on orbital period, with planets that orbit quickly providing more opportunities for observation than those with long years. TRAPPIST-1 planets transit every few days, while an Earth analog around a Sun-like star would transit only once per year. The spectral resolution of the instrument determines what features can be detected, with higher resolution revealing more detail about molecular absorption, but at the cost of spreading the already faint signal across more spectral channels.
Observers must balance resolution against signal-to-noise ratio.
Different molecules have absorption features at different wavelengths, meaning comprehensive atmospheric characterization requires observations across a broad wavelength range. The James Webb Space Telescope's infrared sensitivity provides access to many important molecular features, but some species are better detected at other wavelengths. Clouds and hazes in planetary atmospheres can obscure molecular features, scattering light before it can probe the deeper atmosphere, where gases might be more abundant. Some exoplanet observations have revealed flat, featureless spectra, suggesting thick clouds that block the view of lower atmospheric layers. The interpretation of transit spectra requires atmospheric models that predict what absorption features different combinations of gases, temperatures, pressures, and cloud structures would produce. Comparing observed spectra to model predictions allows constraints on atmospheric properties to be derived. The technique has evolved dramatically since the first detection of an exoplanet atmosphere in 2001, when the Hubble Space Telescope detected sodium vapor in the atmosphere of HD 209458b, a hot Jupiter orbiting close to its star. That initial detection demonstrated that the technique worked. Since then, dozens of exoplanet atmospheres have been characterized to varying degrees with detections of water, carbon dioxide, methane, ammonia, sodium, potassium, and other species. Each detection refines our understanding of how atmospheres work on worlds very different from Earth. The transition from detecting well-studied hot Jupiters to characterizing potentially habitable Earth-sized worlds represents a major step in difficulty, pushing instruments to their limits. Hot Jupiters have large, puffy atmospheres that produce strong signals. Terrestrial planets have thin, compact atmospheres that produce weak signals. The James Webb Space Telescope represents the current state of the art, but even its capabilities are barely sufficient for the smallest, most Earth-like planets in habitable zones. Future telescopes will need to improve on Webb's performance to comprehensively survey potentially habitable worlds. Ground-based telescopes complement space-based observations, accessing different wavelength ranges and providing different types of information. High-resolution spectroscopy from large ground-based telescopes can detect specific molecules and even measure atmospheric winds by tracking Doppler shifts. The extremely large telescope and other next-generation ground-based facilities will significantly improve capabilities for exoplanet atmosphere characterization, potentially detecting biosignatures on nearby worlds that current instruments cannot adequately study. The combination of ground and space observations provides the most complete picture. Transit spectroscopy is not the only technique for studying exoplanet atmospheres, though it is currently the most productive. Direct imaging, where the planet's light is separated from the stars, can also provide spectroscopic information, though it requires extreme contrast ratios that current instruments struggle to achieve. Future techniques might include transmission spectroscopy during secondary eclipse, when the planet passes behind the star, or phase curve observations that track how the planet's brightness changes as it orbits, revealing temperature distributions and atmospheric circulation patterns. The reading of starlight to determine the composition of distant atmospheres remains one of the most remarkable achievements of modern astronomy, a technique that would have seemed like magic to astronomers of previous centuries. The search for biosignatures builds on this foundation, using light as a messenger across the cosmic void, among all the gases that might serve as biosignatures. Oxygen holds a special place in the search for life beyond Earth, not because it is the only biosignature, but because its properties make its presence particularly difficult to explain without invoking biology. Understanding why oxygen matters requires understanding its chemistry. Oxygen is one of the most reactive elements in the periodic table, eager to combine with almost anything it encounters. Given the opportunity, oxygen will combine with carbon to form carbon dioxide, with iron to form rust, with hydrogen to form water, with silicon to form rocks. It is chemically aggressive. This reactivity means that free oxygen, molecular oxygen in an atmosphere, is thermodynamically unstable. Left to itself, oxygen will react with available materials until it is consumed, falling to concentrations so low as to be essentially absent. An atmosphere with significant oxygen must have a source continuously producing it. On Earth, that source is photosynthesis. Plants, algae, and cyanobacteria capture sunlight and use its energy to split water molecules, incorporating the hydrogen into organic compounds while releasing the oxygen as a waste product. This process has been operating for over 2.5 billion years. The amount of oxygen in Earth's atmosphere is enormous, roughly 20 to 1% by volume, representing the accumulated output of billions of years of photosynthesis. Maintaining this level requires continuous production, as oxygen is continuously consumed by respiration, decay, weathering, and other processes. Before the evolution of oxygenic photosynthesis, Earth's atmosphere contained essentially no free oxygen, with whatever oxygen was produced by other processes quickly consumed by reactions with reduced minerals and volcanic gases. The invention of oxygenic photosynthesis changed everything. The Great Oxidation Event, which occurred roughly 2.4 billion years ago, marked the transition to an oxygen-rich atmosphere, a transformation so profound that it has been called the most significant event in Earth's geological history. oxygen went from a trace gas to a dominant atmospheric component. The rise of oxygen reshaped Earth's chemistry, creating new minerals, enabling new metabolisms, and eventually making possible the complex life forms that use oxygen for respiration. The atmosphere we breathe is a product of biology, maintained by biology, and indicative of biology. If we detect abundant oxygen in the atmosphere of an exoplanet, we will have found something demanding explanation, a gas that should not be there unless something is producing it. Biology will become a leading hypothesis, though not the only one, that must be considered. The challenge is that non-biological processes can also produce oxygen under certain circumstances, creating the possibility of false positives, where we detect oxygen but incorrectly attribute it to life. Understanding these abiotic oxygen sources is essential for proper biosignature interpretation. Photodissociation of water vapor represents one potential abiotic oxygen source. Ultraviolet radiation from a planet's star can split water molecules into hydrogen and oxygen. The lightweight hydrogen escapes to space more easily than the heavier oxygen, which can accumulate in the atmosphere. This process is most effective on planets that receive intense ultraviolet radiation and that have lost their water to the hydrogen escape that accompanies it. A planet that once had oceans but lost them through this process might retain atmospheric oxygen as a remnant of its watery past, without any biology involved. Planets around red dwarf stars might be particularly susceptible to abiotic oxygen accumulation, as these stars produce relatively more ultraviolet radiation during their early active phases, and their habitable zones lie close in where radiation exposure is intense. The very stars with the most observable, potentially habitable planets might also be the most prone to false positives. Photolysis of carbon dioxide can also produce oxygen, with ultraviolet radiation breaking CO2 molecules into carbon monoxide and atomic oxygen. Under certain circumstances, this oxygen can accumulate to significant levels, creating an abiotic oxygen atmosphere. The context of any oxygen detection will be crucial for interpretation. Oxygen accompanied by water vapor, methane, and other biosignature gases is more compelling than oxygen alone. Oxygen on a planet that appears to have lost its water is less likely to indicate life than oxygen on a planet with evident surface water. The abundance of oxygen also matters. Earth's 21% is extraordinarily high and would be difficult to explain abiotically. Lower concentrations might be more ambiguous, potentially consistent with either biological or non-biological sources. Scientists have developed frameworks for assessing the likelihood that detected oxygen indicates life, considering the full range of planetary properties that can be inferred from observations. No single measurement confirms or refutes a biological origin. The assessment requires integrating multiple lines of evidence. The presence of ozone can strengthen the case for biological oxygen, as ozone forms photochemically from oxygen, and its detection indicates that molecular oxygen is present. Ozone has strong absorption features in the mid-infrared, making it accessible to instruments like the James Webb Space Telescope. The absence of reduced gases that would consume oxygen also supports a biological interpretation, as it suggests that oxygen production is keeping pace with removal processes. A planet with abundant oxygen despite the presence of reduced volcanic gases must have a very strong oxygen source. Temporal variations in oxygen concentration might also be informative, as biological production often varies seasonally, while abiotic production would typically be more constant. Detecting seasonal oxygen cycles would strongly support a biological origin. The first detection of abundant oxygen on an exoplanet will trigger extensive analysis and debate. As scientists work to determine whether the detection is real, whether the oxygen abundance has been correctly estimated, and whether biological or abiotic explanations best fit the observations. The scientific community will not rush to claim the detection of life, recognizing that extraordinary claims require extraordinary evidence. Multiple independent observations using different techniques will be sought, and all plausible alternative explanations will be carefully considered. This caution is appropriate, given the significance of a confirmed biosignature detection, which would rank among the most important discoveries in human history. Getting it right matters more than getting it first, and the scientific process is designed to eventually converge on truth. The oxygen question illustrates the broader challenge of biosignature interpretation. The need to consider not just whether a signal is present, but what that signal means in the context of a planet whose properties we can only partially determine from light years away. In the next part, we will explore biosignature gases beyond oxygen. The chemical dance that makes life visible across the cosmos. The search for biosignatures extends well beyond oxygen to include a variety of gases that life produces, each with its own production mechanisms and interpretive challenges. Methane occupies a particularly important place in this search, both as a potential biosignature in its own right and as a crucial partner in the oxygen-methane combination. Methane is produced on Earth primarily by living organisms, from the methanogenic archaea that thrive in oxygen-free environments to the gut bacteria that help ruminant animals digest cellulose. Rice paddies, wetlands, termite mounds, and cattle all release methane as a byproduct of biological processes. Like oxygen, methane is chemically unstable over geological timescales, reacting with oxygen and other oxidants until it is destroyed. The methane in Earth's atmosphere would disappear within about 10 years if biological production ceased, meaning its continued presence indicates ongoing production. The atmospheric concentration of methane on Earth is relatively low, roughly 2 parts per million, reflecting the balance between biological production and chemical destruction. This concentration is detectable, but challenging, requiring sensitive instruments and careful analysis. The detection of methane on an exoplanet would be intriguing, but ambiguous, as methane can be produced by non-biological processes, as well as biological ones. Geological processes involving water reacting with olivine-rich rocks can release methane through a reaction called serpentinization. With no biology required, methane can also be delivered to planets by comets and outgassed from planetary interiors, sources that have nothing to do with life. A planet with detected methane might be geologically active rather than biologically active, or might host both processes simultaneously. The interpretive power of methane increases dramatically when it is found alongside oxygen, because these two gases react with each other and should not coexist in significant quantities unless both are being continuously produced. Their coexistence implies chemical disequilibrium, an atmosphere that is not at rest. On Earth, oxygen and methane coexist because photosynthesis produces oxygen, while methanogenesis produces methane, two biological processes that together maintain the disequilibrium. Finding both gases on an exoplanet would strongly suggest that biological processes are operating there as well. Nitrous oxide, commonly known as laughing gas, represents another potential biosignature that would be difficult to explain without invoking biology. On Earth, nitrous oxide is produced primarily by microbial activity in soils and oceans. Bacteria transforming nitrogen compounds as part of the nitrogen cycle. Abiotic production of nitrous oxide is possible but limited, occurring through lightning and certain photochemical reactions at levels far below what biology produces. The detection of significant nitrous oxide in an exoplanet atmosphere would therefore be strongly suggestive of life. Nitrous oxide has absorption features in the infrared that are detectable by instruments like the James Webb Space Telescope, though the expected concentrations on Earth-like planets are low enough that detection would be challenging. A very biologically active planet might produce enough nitrous oxide to be detectable. The combination of oxygen, methane, and nitrous oxide together would be extraordinarily difficult to explain without invoking biological processes. A triple signature that would make the case for life far stronger than any single gas alone. Each gas reinforces the others, the combination speaking more loudly than any individual component. This is why astronomers speak of biosignature gases in the plural. Why the search focuses not on finding one particular molecule, but on characterizing entire atmospheric compositions. The context matters as much as the detection. The relationships between gases as important as their individual abundances. The concept of chemical disequilibrium lies at the heart of how we think about atmospheric biosignatures. The recognition that living planets maintain atmospheric compositions that chemistry alone would not produce. A dead planet's atmosphere reaches equilibrium, its gases settling into stable ratios that persist indefinitely. A living planet's atmosphere is different. Life pushes atmospheres away from equilibrium, producing gases that react with each other, maintaining concentrations that would otherwise decline, creating chemical gradients that persist only because something keeps replenishing them. This disequilibrium is itself a biosignature, a sign that something is actively working against the natural tendency toward chemical rest. The Earth's atmosphere is dramatically out of equilibrium, containing oxygen and methane and nitrous oxide in combinations that would not persist without continuous biological production. An alien astronomer studying our atmosphere would immediately recognize that something unusual is happening, something that requires an energy source and an ongoing process. This recognition shaped how we think about searching for life on other worlds. We look not for specific molecules in isolation, but for atmospheric states that seem impossible without biology, compositions that demand explanation beyond simple chemistry. The equilibrium state of an Earth-like planet with no life would be quite different from what we observe. The oxygen gone, the methane vanished, the atmosphere dominated by nitrogen and carbon dioxide in proportions that reflect purely geological processes. The difference between this hypothetical dead Earth and the actual living Earth would be obvious to any observer with the right instruments. Other gases beyond the usual suspects might serve as biosignatures under the right circumstances. Molecules that we do not typically associate with life, but that biology could produce under different conditions. The search must remain open to possibilities that our Earth-centric perspective might overlook. Hydrogen sulfide, the gas that gives rotten eggs their distinctive smell, is produced by certain bacteria on Earth and could potentially accumulate to detectable levels on planets with different atmospheric chemistry. Its presence would not prove life, but would be consistent with biological activity. Phosphine, a toxic gas composed of phosphorus and hydrogen, gained attention when it was tentatively detected in the atmosphere of Venus, a planet where its presence was difficult to explain through known chemistry. The detection remains controversial, but it illustrated how unexpected molecules might serve as biosignatures. Dimethyl sulfide, the molecule tentatively detected on K218b, is produced almost exclusively by marine phytoplankton on Earth and would be very difficult to explain through non-biological processes. Its detection, if confirmed, would be among the strongest biosignature candidates yet found. Ammonia in an oxidizing atmosphere would be surprising, as ammonia reacts readily with oxygen and should not persist. Finding ammonia alongside oxygen would suggest ongoing production, potentially biological, that maintains the ammonia concentration against chemical destruction. The list of potential biosignatures extends as our understanding of biology and chemistry deepens, each new insight opening possibilities that previous searches might have missed. The universe may produce life that generates biosignatures we have not yet imagined. The abundance of a potential biosignature gas matters as much as its mere presence, because trace amounts might be explainable through non-biological processes, while larger concentrations demand more compelling explanations. The quantitative aspect of detection is crucial. Earth's atmosphere contains about 20 to 1% oxygen, a concentration that is unambiguously the product of billions of years of photosynthetic activity. A planet with 1% oxygen might have accumulated it through water photodissociation, but 20% almost certainly requires biology. Similarly, the ratio of different isotopes in biosignature gases can provide additional information about their origins. Biological processes often prefer lighter isotopes, fractionating elements in ways that leave distinctive signatures. Carbon produced by life has a different isotopic ratio than carbon from geological sources. These subtleties require increasingly sophisticated observations, measurements that go beyond simple detection to characterize the amounts and isotopic compositions of atmospheric gases. The James Webb Space Telescope can detect molecules, but determining precise abundances and isotope ratios pushes current capabilities. Future telescopes will provide this additional information, allowing more definitive interpretation of any biosignatures detected. The goal is not just to find interesting molecules, but to understand enough about them to distinguish biological from non-biological origins with confidence. The temporal variability of biosignature gases might also provide clues about their origins, as biological production often follows seasonal or daily cycles that geological production does not. A gas that varies in concentration with a planet's seasons might be more likely to have biological origins. On Earth, CO2 concentrations rise and fall with the seasons as vegetation grows and dies back. A pattern driven by the biological carbon cycle. Oxygen concentrations also vary slightly, though the variations are small compared to the overall abundance. Detecting such variations on an exoplanet would require repeated observations over the planet's orbital period, watching to see whether atmospheric composition changes as different hemispheres face the star. This is challenging with current technology, but potentially feasible for nearby planets observed over multiple years. The search for temporal patterns adds another dimension to biosignature detection, moving beyond single snapshots to understanding how atmospheres evolve over time. Living planets breathe, in a sense, their atmospheres pulsing with the rhythms of biological activity. The dance of gases that characterizes a living atmosphere is subtle and complex, requiring careful observation and cautious interpretation. No single measurement will prove that life exists on another world. The evidence will accumulate gradually, each observation adding to a picture that eventually becomes compelling. This is the nature of scientific discovery at the frontier, where certainty is hard to achieve and where extraordinary claims require extraordinary evidence. The detection of life beyond Earth would be among the most significant discoveries in human history, and the standards for acceptance are correspondingly high. Yet the dance continues on every living world. Gases cycling through atmospheres in patterns that betray biological activity. Somewhere in the cosmos, on worlds we have not yet observed, atmospheres may be out of equilibrium right now, maintained by life that has no idea we are beginning to look for it. The methane rises from alien wetlands. The oxygen accumulates from alien photosynthesis, and the chemical disequilibrium persists because life persists, pushing against the natural tendency toward rest. We are learning to read these signs, to interpret the dance, to recognize life by the traces it leaves in the air. The search for life beyond Earth has focused primarily on atmospheric gases, the molecules that accumulate in the air and leave spectral fingerprints in starlight. But atmospheres are not the only place where life reveals itself. The surfaces of living worlds can also display distinctive signatures, visible across interstellar distances. On Earth, the most dramatic surface biosignature is the presence of vegetation, the green blanket of plants that covers much of the land surface and produces a distinctive spectral signature called the red edge. This phenomenon arises from the way chlorophyll interacts with light, absorbing visible wavelengths for photosynthesis, while reflecting infrared to avoid overheating. The contrast between visible and infrared reflectance is sharp and distinctive. A sudden increase in brightness right at the boundary between red light and near infrared. This red edge is unlike anything produced by bare rock or water or clouds, a signature that specifically indicates the presence of photosynthetic life. If alien astronomers observed Earth from a distant star system, the red edge would be detectable in the spectrum of light reflected from our planet's surface. The signal would vary as Earth rotated, stronger when continents with heavy vegetation faced the observer, weaker when oceans dominated the visible hemisphere. The red edge as we know it results from the specific pigments that Earth's photosynthetic organisms use. The chlorophylls and accessory pigments that evolved on our particular world, under our particular star. Alien life using different pigments would produce different spectral signatures, and recognizing them requires thinking beyond our Earth-centric assumptions. Photosynthesis on a planet orbiting a red dwarf star might use different pigments optimized for the redder light such stars produce, potentially creating a spectral edge at different wavelengths than Earth's vegetation. The plants might appear black or deep red rather than green, absorbing as much of the limited light as possible. On a planet with more ultraviolet radiation, photosynthetic organisms might develop protective pigments that affect their spectral signatures in ways we cannot predict without knowing their specific biochemistry. The search for surface biosignatures must remain open to unexpected patterns. Theoretical work has explored what various hypothetical photosynthetic pigments might look like spectroscopically, creating a catalogue of possible signatures that observers might search for. This catalogue expands as our understanding of photochemistry and astrobiology deepens, opening new possibilities for detection. The detection of surface biosignatures requires observing light reflected from a planet's surface, which is more challenging than observing light that has passed through its atmosphere during transit. The planet must be imaged directly, or its reflected light separated from the overwhelming glare of its parent star. Current telescopes struggle with this task for Earth-sized planets around Sun-like stars, where the planet is billions of times fainter than the star it orbits. The contrast problem is severe, like trying to see a firefly next to a searchlight from thousands of kilometers away. Future telescopes are being designed specifically to overcome this challenge, using coronagraphs, or star shades, to block the starlight while allowing the planet's reflected light to reach the detector. These technologies are still in development, but they promise to open the search for surface biosignatures on worlds that transit spectroscopy cannot fully characterize. Once direct imaging becomes possible, the reflected light spectrum of a planet can reveal not just what gases are in its atmosphere, but what materials cover its surface. Water, ice, rock, sand, and vegetation all have distinctive spectral signatures that careful analysis can identify. The seasonal variation of surface biosignatures might provide additional evidence for their biological origin, as vegetation coverage changes through a planet's year just as it does on Earth. Deciduous forests lose their leaves in autumn. Agricultural regions are harvested, and the overall green signal weakens before returning in spring. Observing such variations would require monitoring a planet through its orbital period, watching as its appearance changes with the seasons. The pattern of variation could distinguish biological surface coverage from non-biological alternatives, like mineral deposits that do not vary seasonally. Earth's seasonal changes in vegetation are visible from space, detected by satellites that monitor the greening and browning of continental surfaces throughout the year. An alien astronomer with sufficiently sensitive instruments could detect these changes from interstellar distances, recognizing them as evidence of a living world. The combination of atmospheric and surface biosignatures would provide the strongest case for life. Multiple independent lines of evidence, all pointing toward the same conclusion. A planet with oxygen in its atmosphere and the red edge on its surface would be very difficult to explain without invoking photosynthetic life. Bioluminescence represents another potential surface biosignature, though one that would be extremely challenging to detect at interstellar distances. On Earth, bioluminescent organisms light up the oceans at night, producing a faint glow that satellites can sometimes detect from orbit. A planet with extensive bioluminescence might display a subtle glow on its night side that differs from the reflected starlight visible on its day side. Detecting such a faint signal across light years would require instruments far beyond current capabilities. But the possibility illustrates how diverse surface biosignatures might be. The colorful microbial mats that grow in hot springs on Earth produce distinctive spectral signatures that differ from the surrounding rock. Similar communities on other worlds, whether in hot springs or other extreme environments, might produce patterns detectable in the averaged light from a planet's surface. Coral reefs, algal blooms, and other concentrations of photosynthetic life produce localized spectral signatures on Earth that blend into the global average, but that might be detectable on planets where such features cover larger areas. The diversity of biological surface features on Earth hints at the diversity that might exist elsewhere. The interpretation of surface biosignatures faces challenges similar to those confronting atmospheric biosignatures. The need to rule out non-biological explanations before accepting biological ones. Some mineral surfaces produce spectral features that might be mistaken for biological pigments. Certain iron-bearing minerals can produce color and spectral features that superficially resemble what photosynthetic pigments might produce, creating the potential for false positives. Careful analysis of spectral shape and temporal variation would be needed to distinguish mineral from biological signals. The Martian surface provides a cautionary example. Its red color resulting from iron oxides rather than biological pigments, despite early speculation about Martian vegetation. What looks like a biosignature at first glance sometimes has a purely geological explanation. Yet genuine surface biosignatures would be profoundly significant if detected, providing evidence that life has not merely affected a planet's atmosphere, but has colonized its surface in visible abundance. Such a detection would transform our understanding of life's prevalence in the cosmos. The search for surface biosignatures complements the search for atmospheric biosignatures, two approaches that together provide a more complete picture of a distant world than either alone. Living planets reveal themselves in multiple ways, and we are learning to look for all of them. The detection of a potential biosignature on a distant world would be one of the most exciting moments in the history of science. A hint that life might exist beyond Earth. But excitement must be tempered by caution, because non-biological processes can produce signals that mimic what life produces. The challenge of false positives lies at the heart of biosignature science. The recognition that detecting a molecule or spectral feature is not the same as detecting life. Each potential biosignature must be evaluated against all possible explanations, biological and non-biological alike. Oxygen, often considered the most compelling atmospheric biosignature, can be produced through the photodissociation of water vapor in the upper atmosphere of a planet. Ultraviolet radiation from the star splits water molecules into hydrogen and oxygen, and if the light hydrogen escapes to space, while the heavier oxygen remains, oxygen can accumulate without any biology. This process, called abiotic oxygen production, has been studied extensively through theoretical models that explore how much oxygen might build up under various conditions. Planets around certain types of stars, particularly those with high ultraviolet output, might accumulate substantial abiotic oxygen. The distinction between biological and abiotic oxygen might lie in the context, the other gases present, the amount of water vapor, the properties of the star, and other factors that together paint a more complete picture. Oxygen alone is ambiguous, but oxygen alongside other biosignatures becomes more compelling. Methane faces similar interpretive challenges, as geological processes can produce this gas without any biological involvement. Serpentinization, the reaction of water with certain iron-rich rocks, releases hydrogen that can combine with carbon to form methane. This process occurs on Earth and likely on other rocky worlds. Volcanic outgassing can also release methane, as can the delivery of organic-rich material by comets and asteroids. A planet with detected methane might be geologically active, might be receiving cometary bombardment, or might host methanogenic life. Distinguishing among these possibilities requires additional information. The oxygen-methane combination is more robust precisely because it involves two gases that react with each other, meaning both must be continuously produced to maintain their concentrations. But even this combination is not absolutely proof of life, as some researchers have proposed scenarios where both gases might accumulate abiotically. The standards for claiming detection of life will necessarily be high, requiring not just the detection of biosignature gases, but the systematic elimination of all plausible non-biological explanations. This process will take time, involving modeling, debate, and additional observations. The history of claimed biosignature detections provides cautionary lessons about the need for skepticism. The tentative detection of phosphine in the atmosphere of Venus sparked intense interest when announced in 2020. As phosphine on a rocky world seemed difficult to explain without invoking biology. Subsequent analysis questioned whether phosphine had actually been detected at all, with some researchers arguing that the spectral signal had been misinterpreted. The detection remains controversial, illustrating how even careful scientists can be led astray by ambiguous data. Earlier claims about possible biosignatures on Mars have similarly failed to hold up under scrutiny. From the infamous Viking experiments of the 1970s to more recent debates about Martian methane. The pattern suggests that the first claimed detection of extraterrestrial biosignatures will likely face significant challenge before any consensus emerges. This skepticism is healthy and necessary, part of the scientific process that ensures conclusions are robust. Extraordinary claims require extraordinary evidence, and the claim that life exists beyond Earth is among the most extraordinary that science could make. The modeling of planetary atmospheres has become increasingly sophisticated, allowing researchers to simulate what various biosignatures would look like under different conditions, and to explore what non-biological processes might produce similar signals. These models incorporate photochemistry, atmospheric dynamics, geological outgassing, stellar radiation, and other factors that together determine atmospheric composition. By running models with and without life, researchers can identify features that distinguish living from non-living planets. The models are imperfect, limited by incomplete knowledge of planetary processes and by computational constraints that prevent fully capturing the complexity of real atmospheres. but they provide essential guidance for interpreting observations and for designing future searches. As models improve and observations accumulate, the ability to distinguish biological from non-biological signals will strengthen. The current state of uncertainty reflects the youth of the field rather than any fundamental limitation. The importance of context in interpreting biosignatures cannot be overstated. A signal that seems ambiguous in isolation might become compelling when combined with other information, or might be ruled out entirely by additional observations. The properties of the host star matter, as different stellar types produce different radiation environments that affect both the production of biosignatures and the potential for abiotic mimics. Red dwarf stars and sun-like stars present different challenges for interpretation. The size and composition of the planet matter, as larger planets with thick hydrogen atmospheres might produce chemical signatures through processes quite different from what occurs on Earth-sized rocky worlds. Comparing like to like is essential. The presence or absence of geological activity matters, as volcanically active planets might produce gases that dead planets would not. Understanding a planet's interior state helps constrain what atmospheric processes might be occurring. Even the age of the planetary system matters, as young systems might still be in transition, while older systems have had time to reach steady states. The evolutionary history of a planet affects what we should expect to observe. The community of researchers working on biosignature interpretation has developed frameworks for evaluating candidate detections. Systematic approaches that consider all relevant factors before reaching conclusions. These frameworks assign confidence levels to potential biosignatures based on the strength of the detection, the plausibility of non-biological alternatives, and the consistency of multiple independent observations. No single factor determines the assessment. The goal is to avoid both false positives, claiming life where none exists, and false negatives, missing life that is actually present. Both errors have costs, and the frameworks attempt to balance them appropriately. When a compelling biosignature candidate is eventually detected, the evaluation process will play out publicly, with researchers debating the evidence, proposing alternative explanations, and gradually converging toward consensus or continued disagreement. The process may take years, with initial excitement giving way to careful analysis and eventual acceptance or rejection. The patience required is substantial, but the stakes justify the caution. The search for biosignatures will be transformed in coming decades by telescopes and instruments currently being built or planned. Capabilities that will exceed what we possess today by remarkable margins. The future of this search is bright with possibility. The extremely large telescope, under construction in the Atacama Desert of Chile, will feature a primary mirror nearly 40 meters in diameter, gathering more light than any telescope ever built. When it begins operations later this decade, it will be able to characterize exoplanet atmospheres with unprecedented sensitivity. Ground-based telescopes, like the ELT, face challenges from Earth's atmosphere, which absorbs some wavelengths and distorts images. But adaptive optics systems that compensate for atmospheric distortion have improved dramatically, and the ELT will achieve resolutions approaching what space telescopes can provide. The ability to study smaller planets in more detail, to detect fainter spectral features, and to monitor changes over time will all improve with the ELT and other extremely large telescopes being built. The next generation of ground-based astronomy is almost ready to begin. Space-based telescopes offer advantages that ground-based observatories cannot match, escaping the absorbing and distorting effects of Earth's atmosphere entirely. Future space telescopes are being designed specifically for the biosignature search. The Habitable Worlds Observatory, a NASA flagship mission concept currently in development, would be designed from the start to image Earth-like planets directly and analyze their atmospheres for signs of life. The telescope would use a coronagraph to block starlight, while allowing planetary light to reach its detectors. This direct imaging approach would complement transit spectroscopy, allowing the study of planets that do not happen to pass in front of their stars. From our perspective, many nearby potentially habitable planets cannot be studied through transit spectroscopy because their orbital planes are tilted relative to our line of sight. The Habitable Worlds Observatory would expand the sample of planets that can be characterized for biosignatures, potentially examining dozens of nearby Earth-like worlds for signs of atmospheric oxygen, methane, and other gases. The mission is still in the planning stages, with launch perhaps 2 decades away. Even more ambitious concepts have been proposed for the longer term: space-based interferometers that would combine light from multiple telescopes to achieve resolutions impossible for any single mirror. Such systems could potentially map the surfaces of nearby exoplanets, detecting continents and oceans, and perhaps even vegetation. A starshade, a large flower-shaped spacecraft flying thousands of kilometers from a telescope, could block starlight before it even reached the telescope's optics, achieving contrast ratios that coronagraphs struggle to match. Studies have explored how starshades might work with existing or planned telescopes. These concepts remain futuristic, requiring technologies that do not yet exist or funding that has not been allocated, but they illustrate the trajectory of the field, the directions that development might take as the search for biosignatures matures. The history of astronomy shows that capabilities once considered impossible eventually become routine. The detection of exoplanets themselves was considered extremely difficult just decades ago, yet thousands have now been catalogued. Biosignature detection may follow a similar path. The timeline for discovering life beyond Earth, if life exists to be discovered, remains deeply uncertain. The detection might come within years if we are fortunate in our choice of targets, or it might take generations if biosignatures are subtle or if habitable planets prove rare. The James Webb Space Telescope is observing promising targets right now, and results continue to emerge. Each observation adds to our understanding, either detecting interesting signals that warrant further investigation, or ruling out certain possibilities and narrowing the search. The data being collected today will be analyzed for years, reanalyzed as techniques improve, compared with models that continue to develop. A biosignature might already be present in existing data, waiting for someone to recognize it. Or the search might continue for decades, through the lifetimes of telescopes not yet launched, before definitive evidence emerges. The patience required is substantial, but the question is important enough to justify the investment. The value of the search extends beyond any particular detection, teaching us about planetary atmospheres, about chemistry, about the conditions for habitability, even when biosignatures are not found. Negative results are still results, constraining the prevalence of life and the conditions under which it might arise. If the search continues for generations without success, we will learn that life is rare, that the conditions required are more restrictive than we assumed, that Earth may be more unusual than we hope. This too would be significant knowledge, reshaping our understanding of our place in the cosmos. But if biosignatures are detected, if the evidence accumulates to the point where the scientific community accepts that life exists on another world, the implications would be profound. We would know that life arose at least twice in two independent locations, suggesting that it might arise wherever conditions permit. The universe would be transformed from a vast emptiness with one lonely island of life to a cosmos where life is a natural outcome of planetary evolution. Our own existence would seem less accidental, more expected, part of a larger pattern that extends across the galaxy. The night continues wherever you are, and the thoughts of biosignatures and distant worlds can settle now, becoming atmosphere rather than information. The telescopes continue their observations, gathering light that has traveled for years, searching for patterns that might indicate life. The James Webb Space Telescope orbits the Sun at the second Lagrange point, 1.5 million kilometers from Earth, its golden mirrors catching starlight that passed through alien atmospheres months or years ago. The data streams back continuously. Ground-based observatories open their domes as darkness falls across their mountain-top locations, preparing for another night of patient observation. The accumulated data grows, the analyses proceed, and the understanding deepens gradually. Somewhere in this workflow, perhaps already in hand, or perhaps years away from collection, the first definitive biosignature may be waiting to be recognized. Or perhaps the search will continue far longer, the universe proving more subtle than our current methods can penetrate. Either way, the search has value, focusing human attention on one of the deepest questions we can ask. Are we alone in the cosmos? Or does life arise wherever conditions permit? The question deserves the patience that answering it requires. The fingerprints of life, if they exist on other worlds, wait to be found. The gases accumulate in alien atmospheres. The pigments color alien surfaces. The chemical disequilibrium persists because life persists. We are learning to read these signs. The search continues while you rest, telescopes pointing at distant stars, instruments measuring spectra, scientists analyzing data. The patience of the endeavor matches the patience appropriate for this hour. The slow accumulation of evidence, the gradual approach toward understanding. Whatever the cosmos contains, life abundant or life rare, or life only here, the search itself connects us to something larger than daily concerns. We are asking the universe about its contents, and we are building the tools to hear its answer. Good night from the Drowsy Astronaut. Sleep well, and we'll explore the cosmos together again soon.